You're going down! Oh, hi. Didn't see you there, sorry. Me and my friend were LARPing. It's actually pretty fun. You know what, why don't we go inside and I'll tell you all about it. In 413 BC, the first reported case of LARPing was found. This was called Spartans and Athenians and was often done by children during the Spartan-Athenian War. This has transcended through the ages in the form of cops and robbers, cowboys and Indians, house, and it's often played by children. It's a very simplistic form of LARPing and doesn't really involve rules or structure or long-term gameplay. It's not really very close to the LARPing that's done today by adults, but it's still the first reported case of LARPing, and it's therefore important in that sense. Adult LARPing is very different from kid LARPing in the sense that it's not very fantasy-based, and it's more real-world applications. A lot of time, police and military organizations will have their new cadets or trainees storm a building or defuse a hostage situation. This will have real-world implications on a policeman's career, and if they fail, they might not even graduate. Military organizations will do this so that if their actual recruits have to go into battle, they will not get shell-shocked and they will be able to think more in stressful situations. This can significantly help improve their chance of survival in a firefight. Adult LARPing is very different from kid LARPing, but is still, in essence, a type of LARPing. In the 1920s, LARPing started to become more popular with the forming of the Mobile League of Nations Club. This was a LARPing-based club that started forming around the country independent of itself. They would often LARP in urban places, or forests, or just the streets. In New York, also, assassin-based LARPing started to become popular with a small, close-knit group of friends essentially killing each other on a regular basis. Over time, this became more popular, especially in the 1970s with the first publishing of the first Dungeons & Dragons book. As a dungeon master myself, I can say that this has a very heavy fantasy-based gameplay and makes you want to do real-life actions as well as just on-the-board games. Anyway, now let's talk about the physics of LARPing. So anyway, as you can see modeled by this whiteboard, the linear motion problem is graphed here. Now, usually in LARPing, there are two different types of melee weapons. There's swords, and there are bow and arrows. Now, as you can see from this bow and arrow, a projectile, the arrow, is shot off with a certain amount of velocity and force behind it, at an angle. Now, for this example here, my friend Chaddington over here is shooting an arrow at a 30-degree angle at 100 meters per second, which is the average speed of a shot arrow. So, for the beginning of this equation, first we'll model the arrow's flight. This triangle here models out the whole arrow's flight. Now, for linear equations in physics, you can't actually have an angled path, as you can see here. So instead, we have to find the relative x-axis and y-axis values. In making a 30-60-90 triangle in basic geometry, you know that this angle here will be shooting upwards at 50 meters per second, and this one here will be shooting at 50 meters times the root of 3 meters per second. And using this and the kinematic equations down here, we can actually model out the area of the graph and find out where it will land, where its maximum height will be, and stuff like this. Now, these two equations here are kinematic problems. The variables listed below are distance in meters. This is the initial velocity of the arrow. So for the x-axis, as modeled over here, it'll be 50 meters times the root of 3, or the y-axis will be 50 meters upwards. This here is acceleration for the natural acceleration. So for the y-axis, it's the gravitational constant, which is negative 9.8, or 9.8 downwards, and the time of the total flight of the arrow. This equation here can also be used for different variables. This is the final velocity of the arrow. This is the initial velocity of the arrow, as we talked about above. The gravitational constant for the y-axis. For x-axis, there's no acceleration, negative or positive, and the total time of the arrow. Now, using this, we can model this equation here. Let's say you want to find out the maximum time the arrow is going to be in the air. Well, you can use these equations here. Now, using this equation here, we'll be able to find the total time the arrow is in the air. Starting off, we have the final velocity of the arrow, which is 0 meters per second, because at that point, the arrow will have hit the ground or have stopped moving. Now, we'll start with the initial velocity of the y-axis, because we're finding the maximum time of flight. The x-axis theoretically would go on forever, because there's no end set time. We'll also be using the acceleration for the y-axis, which will be negative 9.8 meters per second. Or also, as you could see
50
meters per second upward and 9.8 meters per second downwards. So, to start off, we plug those values in to get this equation here. Through a fairly simple process, we'll find that's 5.1 seconds. As you can see here, 5.1 seconds isn't the actual end of the flight of the arrow, it's the maximum height of the arrow, or the time at which the height will be maximum. This is because there's no more upwards or downwards force on it. Essentially, both velocities cancel each other out. What?
There's still a downwards force on it, man.
Yeah, but like there's no current downwards force.
There is. It's gravity.
At this point in time, the object will have no upwards or downwards velocity, but it will have a downwards acceleration still. Thanks, Megan. But anyway, so by simply doubling this time, we'll actually get to the end point here. So at 10.2 seconds, the arrow will have hit the ground, so that'll be the end of its flight. So I'm just saying, how did you get 127.5 meters as the maximum height, which I have written here. Well, as you can see, but why 127 meters? So to do this, we actually use the distance canonical formula. This is the total distance. This stands for the total distance. This is the initial velocity. This is the time, which we know to be 5.1 seconds because that's the time we found out for this. This is the initial velocity from before. This and 1/2 acceleration, which is negative 9.8 meters per second, and time squared, which we've also established as 5.1 seconds. So plugging these values in, we simply do the formula out, as seen here, to get 127.5 meters. That would be the maximum. That would be the maximum height of the arrow. But so that's the relevant equations, and that's the flight time. If you are wondering how far will it go on the x-axis or how far forward will it go, we have that model over here. We use the same formula as before for distance, except on the x-axis. So instead of using 50 meters per second, we use 50 times the root of 3 meters per second times the maximum time, not the middle time. Because there's no acceleration on it, the a value here will be 0. So essentially, it would just be 50 to the root of 3 times 10.2. So in conclusion, the arrow's maximum height will be 127.5 meters, and the total distance it will travel on the x-axis will be 883.3 meters. Anyway, let's go outside to do a real-life example of kinematics, kinetic energy, and potential energy. Well, anyway, let's go down there and get a closer look at the action, huh? Anyway, over here we'll be doing a series of tests on Kevin. He's my LARPing companion and he's a good friend. Kevin, how are you doing? Good. So in today's example, we're going to be dropping a series of objects on your head to test the kinetic and potential energy and also the end velocity. We'll also be doing this to get kinematic examples of time, okay? So my LARPing friend Kevin is going to try and get into my castle. Now, I don't want that, so I'm going to be dropping some objects on his head to make sure he's not able to get in. So, before this video, I took some measurements relative, and we found out a few things. My castle right here is 258.5 centimeters tall. Kevin is 179 centimeters tall. Between him and the castle, there's 79.5 centimeters worth of space. Now, to prevent him from climbing the castle, I'm going to be dropping stuff on his head to make sure he's just unable to. I would usually use pretty heavy rocks, but he is my girlfriend's brother, so I guess to be nice, I'm using this light foam ball. The weight of the foam ball, as shown in this video, this clip, is 11.34 grams. Now, if you got that equation at the top of my head, after I kill Kevin, I'll be writing that equation down, showing you the exact values and potential kinetic energy. Now, Kevin, say your prayers. Now we're going to be doing a real-life example of a kinematic equation. As you can see from the formula over my head, the time it should take for this jug to hit the ground is 0.726 seconds. This is done based on distance and relative gravitational constant. My assistant Megan over there will be taking the total time on her stopwatch of the first tick again. So I'll be dropping it on, in a second. Megan, are you ready?
Yeah.
Okay. 5, 4, 3, 2, 1. So now, what time did we get?
0.73 seconds.
As you can see from the 0.73 seconds, we were slightly off due to basic human error and the fact that Megan could not click it perfectly on time. But that is close enough for us to assume that it did take 0.726 seconds to hit the ground. This is an example of kinematic equations and how they have real-life applications and do work in real life. Anyway, let's go inside and I'll tell you all about the potential and kinetic energy situations. Oh my god. So, for potential potential energy equations, you'll often have a case where one guy, this guy right here, will be throwing something at someone else, or dropping an object. Now, in LARPing, this is relevant if I want to drop a rock or something on my assistant's head, as you saw earlier. He's okay. The tackling, which you're going to see in a little bit, was, might be a little bit hurt, but whatevs, you know, he signed a waiver, so it's okay. Anyway, so for this example, we're doing the one outside where I dropped the ball on his head and he turned into triangles. So, first of all, we have the actual castle I was standing on, which was 258.5 centimeters tall. Next, we have Kevin himself, who was 179 centimeters tall, and the space between us, which is 79.5 centimeters tall. The mass of the ball, as was weighed, was 11.34, as you saw in the other video. Anyway, now, potential energy and kinetic energy. This is very important. Potential energy is always going to be equal to kinetic energy at the end, or they will balance each other out. So if you have 100 potential energy and no kinetic energy, at the end of the equation, when the ball is about to hit the ground, it will have 10 kinetic energy and 0 potential. Vice versa, if you had 5 potential energy, there would be 5 kinetic energy as well. This is very important because it makes equations much easier, and it means that potential energy is equal to kinetic energy. So, for this equation itself, we simply put the variables in here. This is mass, height, and gravitational force. So we multiply the mass, which was 0.01134 kilograms. It's in kilograms, that's why it's 0.0 and not 11. The actual height in meters, so it's 0.795 meters, and the gravitational constant, which is 1.8, and we multiply that to get the energy potential energy, that obviously. But, so basically, we multiply those, as you can see here, and we get that the potential energy is 0.088 joules. Not very much, so we know that Kevin will not be seriously injured. Now, if the mass was greater, Kevin might be injured. But luckily the mass was smaller, so Kevin will be fine, probably. Tackling, seriously, he's a good boy. We just hope for the best, honestly. Yeah, okay, so anyway, going here, now we can find the actual velocity of the ball at the end of its route. We know the end energy in joules here, so we actually just plug that in, and then for the mass we already know, so we just do the equation here. As you can see, it's 2, and the mass and the velocity value over 2 equals 0.088 joules. We plug that in, and we get the end velocity when the ball hits Kevin is 3.94 meters per second. So we know that Kevin's going to be uninjured. Now, we're going to go outside and do an example on inelastic collisions, which will involve tackling Kevin, as I mentioned. So anyway, let's go. Anyway, let's talk about inelastic collisions. Anyway, as you can see from this diagram here, an inelastic collision and graph is drawn out for you to observe. Now, these diagrams here on the whiteboard graph out an inelastic collision for you to actually be able to see and, observe. So, for this, we're going to be doing a fairly simple one of an 80 kilogram mass hitting a 60 kilogram mass at 13 meters per second, okay? As you can see, the resulting, force is written here, but we don't actually know the resulting in meters per second of both objects, so the end velocity. Now, the equation to do this is actually fairly simple, written out right here, okay? So, we have the mass of the initial object, the velocity of the initial object, plus the mass of the second object and the velocity of the second object, which will equal the mass of both objects combined and times the end velocity. Now, written out here in the equation, we can see that it's the mass of the first one, so 80 kilograms, the velocity of the first one, 13 meters per second, plus the mass of the second one here, times its velocity, which is 0 meters per second. So essentially this part of the problem is equal to 0. This will equal the mass of both, or 80 kilograms plus 60 kilograms, times the final velocity. This is the variable we're trying to find. Now, adding this together, these two multiplied equal 1040, and which will equal 140 times the final velocity. This gives us the end answer of 7.43 meters per second, equaling the final velocity. Now, as some examples of an elastic collision, we're going to be showing my assistant getting tackled repeatedly. Tackle 1. Tackle 2. Wow, that's pretty crazy. Tackle 3. Tackle 4.
Level 5.
That's all. That is everything, folks.
Hunger Games, I wanna win it all. I wanna win all day. I'm not teaming. You should've learned how to play. Yes, I win it all, so I win it all. I wanna win all day. I'm not teaming. You should've seen my last Hunger Games.